Welcome to problems 3 and 4. I've been told it's going to get real. If you printed this out at home, which you don't have to, it should look like this if your printer was messed up like mine was. So let's just get rid of that. If it makes you feel better, you can draw like near. I hope that's enough room to do the problem. If not, I'm going to look silly. Oh man. Seeing that on the screen, that does not look as much like a perfect rectangle as I imagined it. All right, well, if little things like that bother you, you might as well just skip ahead to problem 4. That one will look a little bit neater. Okay, so projectile has initial velocity of 10 meters per second at an angle of 37 degrees. They give us the range, 15.6 meters. What was its launch height? So here, we're using all the same rules of projectiles, but we're just working backwards a little bit. Things will be slightly different, but something tells me we can handle it. If we have the range and the initial velocity, we can work backwards from those to try to put some pieces together. And then eventually at the end, we're going to use our y stuff to get the height. So sort of reverse process like usual. Okay, so with let's set up our velocity here. So we have 10 meters per second and break that into x and y components. 37 degrees. Here we go. So we've got Vy and we have a Vx. So this will be 10 cos 37. Opposite side is going to be 10 sine 37. Like woohoo, like usual. Wait, that's not a calculator. That is a calculator. You can't fool me. All right, so 10 sine 37. Bingo. 6.02 times 10 to the 23rd meters per second. It's a little chemistry joke there. Sorry about that. And 10 cos 37. 7.99 is the x velocity. Then if we look at our range kind of stuff, if we know the range and we know the x velocity here, we can put those together to find the time. So we would have range equation. So we know the range over here is 15.6 meters. We know the x velocity is 7.99 meters per second. We don't know the time, but we can figure it out. Notice if you take a peek at the units, if we take units of meters divided by meters per second, that gives us a time in seconds, which is neat because that's what we're going for. We like when our times are in seconds. 15.6 divided by 7.99, 1.95 seconds is the time. Then we can set everything up in the y equation using that great quadratic-y looking kinematics thing. Try to figure out the delta y. So the equation is usually written, I'll do this in y version, but you have your y and your y naught plus a bunch of stuff over here that I'm not going to copy down right now. If you want, you can just move this over to the other side, do y minus y naught, and call that a delta y if you want. That'll help us find the height. And just set that equal to everything else we know. So the next part of the equation is the initial velocity in y times the time. So that is our 6.02 times our time of 1.95 seconds plus 1/2 times the acceleration in y. Make sure that's negative. Acceleration should be downward. Times t squared, 1.95 squared. And then we can get our delta y just by typing into a calculator here. 6.02 times 1.95. Okay. That's obviously very wrong. So I think I'm going to have to restart this video. Oh, no. When you type it in correctly, you get negative 6.91 meters. Negative, is that a problem? No, actually, in this case, that makes sense because that's the delta y. So the change in y means you started at an initial y, and if you hit the ground at a point lower than you started, delta y should be negative, which just means the initial launch height, call it h or z or w, whatever you want, is going to be 6.91 meters. That's why you got to type stuff in your calculator. We'll hop on over to the simulation and see how we did. So I put in the launch height that we calculated. 6.91 meters is pretty close to 7. 37 degrees was given. 10 meters per second was given. So if we use our calculated height with the given launch angle and velocity, we should be able to hit a target at 15.6 meters with, what are we shooting here today? Looks like a piano. All right, too close. There you go. Sing us a song, Billy Joel. You are the piano man. 3 stars, broken piano. Physics broke that piano. Actually, probably would have broken anyway, even if you got the calculation wrong. But feels good to at least get the target. All right, see you at the derivation, folks. Our last question today is a derivation. So you might have seen some of these last year if you took AP Physics 1. These are things that'll sneak in from time to time in AP Physics 2 as well, where they're going to ask you to solve for an equation symbolically or algebraically without giving you any numbers. So they just want you to come up with some expression for whatever situation they're describing. We'll practice this several times over the next couple labs this week and next week, but it's a really important physics skill. You basically, if you're not familiar with this, just use the equations, and instead of plugging in numbers, you just keep variables there and hope they simplify to something pretty. Sometimes they do, sometimes they don't. This one's okay, but it's not nearly as nice as the one in Review Lab 2. And if that's not incentive enough to do Review Lab 2, then I don't know what is. I promise that is a spiffy derivation. So anyway, it says derive an equation for the range delta x of a projectile fired horizontally, thank goodness, in terms of constants in the following variables, launch height and initial velocity. So treat this like a horizontal projectile problem like we've been doing for, I don't know, however long we've been doing it. And let's look at the y direction. So in the y direction, the initial velocity is 0. So if we plug variables into our equation, this is the second kinematic equation from page 1. So the final y coordinate is 0. The initial y coordinate was the launch height, which is h. The middle term is going to boil down to 0 because this is our initial velocity in y. And plus 1/2 times the acceleration in the y direction is negative g. Let's use a g here. I know you're tempted to put 9.81, but if they want a derivation, usually it's going to look a little cleaner. And if you just put a g instead of an actual number, you can take this equation with you to any planet you want, or moon, or whatever, and just swap in a different value for g. Negative because the acceleration is downward, and t squared. So we can use all of this to solve for the time, which we'll need. If you didn't know that you needed it, if you look at the range equation, it's the x velocity times time. So we don't have time in these required variables over here. So this will help us get there. So anyway, we have negative h equals negative 1/2 gt squared. So we can make those both positive. Multiply by 2, divide by g, equals t squared. Then if we want to solve for t, just take the square root of 2h over g. Neat. And then we can just substitute in over here. We have delta x, the range equals x velocity. They just said we can use v for that because all that velocity is in x, times the square root of 2 times h divided by g. All right, so there is our expression. So why is it useful to have this skill? One, it's cool, makes you look like you actually know what you're doing with physics, which, it's a little icing on the cake. Two, they might actually ask you to do this in an AP question, or maybe I'd ask you to do it on a test or something like that. Three, it's really nice. So if you're going to do multiple calculations, multiple launches, or multiple trials, you have your equation set up already. All you have to do is plug in the different variables for velocity, height, and g. And why don't we just see if this thing actually works? So let's just pick some random numbers here and head over to the simulation and see if it'll work. Let's use our initial velocity of, 12 meters per second. Let's have a launch height of 12 meters. And I think the simulation actually lets us change the value of g. So let's do like a low gravity situation. Maybe it's only like 5.6 meters per second squared. So according to that, plugging numbers into our equation, we have velocity would be 12 times the square root of 2 times 12 divided by 5.6. And that predicts that the range is going to be 24.8 meters. Let's see if it's true. Here is our setup. Notice I put in all the constants that we just picked and all the variables that we chose. So 12 meters horizontal, 12 meters per second, and I set gravity to 5.6 meters per second squared. The equation that we made all by ourselves says it should have a range of 24.8, and splat, we got it. That was a baseball I fired because it's baseball season now, I guess. It's not a hockey puck because the Blue Jackets lost and they're out of the playoffs, but that's a whole nother thing for another time. At least you can still depend on physics.